ultracold collisions of highly magnetic atoms.
Yeah. First, I would like to thank the organizers for inviting me for this very interesting meeting, and also allowing me to present our work on ultracold collisions of highly magnetic atoms. Okay, sorry. So our collaborators are Francesca Ferlana's group from University of Innsbruck, and Aita Stissinger is here from NIST and JQI, and here people from my group at Temple University who contributed a lot in this work. So most of ultracold atom experiments are performed with alkali earth atoms, alkali metal atoms, which has one s electron on outer orbital, and they mostly interact by van der Waals interaction, which falls very quickly with a distance between atoms, and quite often this interaction could be described with just effective delta function. And this interaction is anisotropic, and it does not depend on the angle of approach. In contrast, interaction between atoms with large magnetic moment, or even molecules with field-induced dipole moments, are dipole-dipole interactions. They depend on the angle, direction at what atoms approach each other. Good candidates for dipole-dipole interactions are, first of all, heteronuclear molecules with field-induced electric dipole moment. And recently, several groups, or I would say mostly two groups, created ultra-cold, high phase space density molecules, potassium rubidium and rubidium cesium. This is Gila group and group at Innsbruck University. Then magnetic atoms also have large magnetic dipole moment, and there are some also successful experiment to cool and trap these atoms and create very high densities. And then you can mention Rydberg atoms, which have very large electric dipole moment. It's actually dipole-dipole interaction for Rydberg atoms is the strongest one. And then it follows by heteronuclear molecules, and then the smallest actually, but not small, it's between magnetic atoms. So I am going to focus on high-spin atomic systems. There are some advantages to use atomic systems in optical lattices, even in optical traps, for performing experiment. Since you know, ultra-cold molecules, you have to still stabilize them. You practically have to create molecules in the absolute ground state, where dipole moments is the largest. You can initiate the largest one, and then you perform whatever experiment or chemical reactions experiment or many body states experiment. This is for ultra-cold magnetic atoms. They already there. You know, there are some other problems, but at least it's much more simple to start to work with them. So their development started from chromium atom, which was created, first cooled and trapped by Tiemann Pfau group at Stuttgart University, and then 2005 this atoms BEC was created. And this atom has magnetic moment of 6 Bohr magneton. So then development followed by researchers from University of Illinois, and this group moved actually to Stanford University later. It's a group of Professor Benjamin Lev. They also formed a BEC of bosonic dysprosium atoms, temperature 30 nanokelvin first. And that follows almost immediately by group Professor Verlaine at University of Innsbruck. They prepared BEC of bosonic erbium atoms, and they followed creation of also quantum gases of other bosonic isotopes and also fermionic isotope. Only one exists for erbium. So dipole-dipole interactions lie in the heart of interesting physics, complex spin dynamics. For chromium, there are more experiments. It started, since 2004, 2005. It's already quite long period past. So interesting experiments performed in groups of Tiemann Pfau and Laboratory Tollera from France. So I give just 2 examples where dipole-dipole interaction could be interesting and important. For example, a group of Laboratory Tollera, they observed spontaneous magnetization of the sample of chromium atom when they decrease temperature, create BEC. So practically due to dipole-dipole interaction, chromium atoms distributed among different magnetic sublevels, but when you decrease temperature, they actually go into one lowest magnetic sublevel. Then also spin dynamics.
What drives this process?
Of course, it's a combination of temperature and dipole-dipole interaction. So spin dynamics was also interesting, observed for, again, chromium atoms in optical trap, I think, in experiment of Pfau, when they converted magnetization converted to rotational properties of the BEC. So it's actually due to dipole-dipole interaction, orbital, a spin is coupled to orbital momentum, and an experiment they observed sort of rotation of this BEC and also kind of pictures similar to vortices. In our work later, we analyze interaction between dysprosium atoms, and we also predicted that similar effect could be observed in dysprosium. So again, it is dipole-dipole interaction allows to, create different exotic many-body phases, and it was predicted for strongly magnetic atom that superfluids, liquid crystal, and quantum ferrofluids could be created. And then finally, a long character of dipole-dipole interaction can be used to entangle 2 or more atoms, magnetic atoms placed in optical lattice, where Zeeman sublevels could be bits and in uniform magnetic field. So here's outline in my talk. So I will focus on dipole nature of Feshbach resonances in interaction between highly magnetic dysprosium and erbium atoms. That was originally, when we started this work, practically nothing was known about interactions between these atoms. Not much known even the electronic structure of two atoms together. So that's what I talk a little bit about our work on produce realistic properties of this system. Then, based on exact close coupling model, we determine likelihood of resonances, Feshbach resonances, and the density as function of magnetic field. So I explained why, maybe not in this point, but we actually perform statistical analysis of distribution of these resonances in magnetic field on the separation between neighboring resonances and compare these properties with experimental data. And then we also develop random quantum defect theory to estimate mean resonant densities as a function of partial wave. And then finally, we also calculated and analyzed magnetic dipole moments for different Feshbach resonances of erbium, and then compare again with experiment. So a few words about the structures of dysprosium and electronic structure of dysprosium and erbium. So dysprosium is a rare earth atom which has unfilled 4F10 shell lying beneath filled 6s2 shell. So this structure leads to very large orbital momentum of this atom and total J orbital momentum 8. So the ground state of this atom, far away from S state, it's a 5I8 state, and the magnetic moment at 10 Bohr magneton. It's of course due to unfilled F electrons, this aligned and two relativistic suborbitals. So I will show also potentials, but in principle, there are 153 electronic potentials of dysprosium-2, which can dissociate to the same atomic limit. So it's very complicated system.
You said 153. Is there an easy way of seeing that from the numbers that you've given up there?
Yeah, if you you have to sum together, several open F electrons outside of closed shell. Then you have to sum together, and each F electron is J is 5½ and 7½ So I think outer shell is 7½ practically. 5½ is lower, and then 7½ on the top, and that one is open. And when you start to sum together, you're not like summing 714, right? You have to sum from 0 to maximum value, like plus minus, right? So it creates a lot of states. And
the J is 8, so
and defined actually.
So 17 squares already good, I guess.
Yeah, and actually, yeah.
17 squared over 2, maybe?
Yeah.
Yeah, you can look at J as well, right? It will tell you immediately.
Okay.
So here's what I want like to say here that it's actually both erbium and dysprosium are relativistic atoms. Because they are heavy, but also the structure suggests that you cannot use non-relativistic electronic structure calculation to predict potentials. Because, for example, so here I show erbium atom few configurations. The lowest one, ground state configuration, and then there are few excited state configuration. In every box describes group of energy levels that belong to this configuration. So in this work, we are interested in the ground state that lows the very low energy, the lowest at the bottom of this box. But if we calculate, say, potentials from interacting two atoms like this, then non-relativistic calculation will give us potential that converge somewhere to-thirds approximately of this box. It would be absolutely wrong long-range behavior and wrong energy. So for these particular systems, we need to perform relativistic calculation.
So what are your units?
Huh?
So this is energy measured. So what are the units? Centimeter minus?
Units in wave numbers, minus centimeter minus 1.
So it's a wave number or something.
Yeah, it's wave numbers called, right.
Do you have the conversion to maybe EV?
Electronavolt?
No.
I think 8,000, right? Electronavolt.
Well, I know that molecular spectroscopists
Ah.
love wave numbers, right?
Yeah.
But atomic people might like EV.
EV and maybe atomic units as well sometimes, yeah. Yeah.
Okay.
You know, nowadays spectroscopy and even a cold collision physics experiment, they need precision up to few wave numbers. So electronavolt will not work. I mean, of course, you can say 10 to minus 8, but my experience shows. So it's useful actually for even experimentalists. So here's something about properties of these inelastic collisions of these atoms. Originally, sometimes, long time ago, people thought that this is very nice atoms that inner shell is protected, but by close outer shell, therefore they should have very small inelastic losses. For some reasons, some like having optical clock or whatever other reason. So that was expected because they have absolutely closed symmetric outer shell. And in experiment first performed by John Doyle group, and I think there are a few more groups, when they looked at collisions of this kind of atoms with helium, then they found indeed the inelastic collisions are small, much smaller than rates, much smaller than for alkali metals. But later, like 2010, John Doyle performed an experiment, look at the collisions between two or between the same rare earth atoms. And they actually call it submerged 4F shell atoms. And they found it is not true anymore. The inelastic collisions collision rate is quite high. It's practically the same as for alkali metal atoms. And the possible explanation is strong anisotropy in interactions. So, as example, how strong anisotropy due to 4f electrons could be, I just showed that angle variation of 4f shell function. And you can see for different projections of the total angular momentum, shape of a function is absolutely different. And when atoms with different shapes approach each other from different directions, which defined by this m, l value, they interact differently. So I start to analyze the interaction from a long-range interaction potentials. There are 3 dominant long-range forces for these magnetic atoms. So one force, of course, is magnetic dipole-dipole interaction, which falls with distance between atoms as r to the 3. So, but there is also dispersion interaction. This dispersion interaction, a little bit more short-range interaction, but it's always present, and it has several kind of terms, and there are terms which describe isotropic contribution to this interaction, and there are anisotropic terms. And anisotropic terms we found mostly the largest terms are related to coupling between quadrupole moment of each atom with rotation of a molecule. It's very important part, specific properties which give interesting anisotropic interactions for these particular atoms. And of course, electric quadrupole interaction is possible, and it depends on the electron quadrupole moment of the atom, each atom, which was not known for this particular atom, so we have to calculate it. And we found actually they are quite small. Quadrupole moments are small. And I will show some value later. So a little bit more details about calculating dispersion interaction. So about magnetic dipole-dipole interactions, easy magnetic moment is known, so we just already know the value, size of this interaction. But dispersion interaction was not known at all. So we use second-order perturbation theory in dipole-dipole interaction, summing over all excited atomic states to calculate CC6 coefficients. And we derived full van der Waals Hamiltonian, introducing through the product of 2 matrices. One matrix, of course, angular momentum matrix, and second one, the matrix, K matrix. It depends on atomic transition frequencies in oscillator strengths, which we decided to take from experimental data. And of course, we can base this data on our theoretical calculation, but it's quite complicated spectrum, and uncertainty is pretty large. And from the other hand, there's a lot of experimental data on dysprosium and erbium, because these atoms are used in the lighting industry to create very, very exotic lights, night vision, whatever it is. So, and I think it like 20, 30 years ago, some experimental groups worked on spectroscopy of these atoms. And there are tables that we can use. So we used like 62 transitions. But of course, not only frequency transition, we need oscillator strengths or dipole moments as well. So here I show what we obtained for, first we looked at the adiabatic C3 and C6 coefficients, which correspond potential like dipole-dipole interaction potential or dispersal potential. You just divide by out of the 3 out of the 6. Here is for dysprosium, interacting dysprosium. So here I show only Gerada symmetry potentials because in experiment we have spin polarized bosonic atoms. So they're sort of the same atoms and they only collide in Gerada symmetry states. Omega is a projection of the total angular momentum of 2 atoms on a body fixed axis. For now, we looked first at the body fixed axis, and then we will go to other axes later, this specific transformation. So here is a C3 as a function of this omega. Practically, omega describes the different directions which atoms approach each other. It's a projection, so there are different projections. For omega equals 16, there's only one potential. But if we, decrease omega, there are more and more potentials. And for 0, there are, many more potentials with the same omega. But they will have different C3, and they could be positive, negative. It means atoms are, attracted to each other or repulsed, dependent on the direction of approach. So number 81, Gerada potential, so 81 of these circles. The same 81 circles for C6 coefficient, but that has more kind of funny shape. And then it's always positive. It was always attractive, C6 potentials in this system. So same sort of idea for erbium, interacting 2 erbium atoms. Yeah, here I say it, right? Should say it before. So behavior of a C3 coefficient, even erbium atom has slightly smaller magnetic moment. So that's maybe values smaller, but sort of, kind of behavior pretty similar, how it's spread over omega. And I put this shade over to show how big anisotropy is. Practically, anisotropy, it's a difference between like biggest and smallest value of the C3. So possibility to have so different values, that's what I want to show here. So here also C6 has different kind of shape. It's practically, I would say, opposite sign. But also, I would like to point out that C6 is much larger, anisotropy in C6 is much larger for erbium than for dysprosium. And we don't know why. It's just a result of the structure. I hope we will maybe understand later when we work on these systems even more. So here I just compare different sizes of these interactions. It's kind of useful sometimes. So, but I also added here on this graph Zeeman splitting. So I kind of started to look at the rotation of atoms and also behavior in magnetic field. magnetic field is very important ultracold physics. Sometimes magnetic field used to trap atoms, but quite often now atoms trapped in dipole traps, optical traps, but magnetic field then used to control them. So here on this graph, I show two lines, dashed lines, for size of the splitting of two atoms, splitting of the energy levels for 1 Gauss and 100 Gauss. And then I also show C6/6 as isotropic potential, and then magnetic dipole-dipole interaction potential, and anisotropic C6 potential. Here, quadrupole interaction is very weak. It is present in our model, but it doesn't really influence anything. So I just want to tell that in this a model or this kind of system, what we consider Zeeman rotation and isotropic dispersion interaction can shift levels, but cannot induce spin flip or mixture between different Zeeman sublevels, for example, which is very important here. So, but anisotropic interaction, this C3/3 or dispersion can mix levels. It can cause spin flip and can cause inelastic decay or a loss of atoms from the trap.
You may have said that, but what's the difference between the C6, the blue curve, and the purple curve, which is the delta C6?
Yeah. Well, if you remember, it was expression for dispersion interaction potential. It has different terms. There's isotropics, which we accustom very much, C6 coefficient, Wonder-Wise. But it has actually an isotropic part. And sometimes in these atoms it's very, very important. They have such a large L orbital momentum, and it supports to have anisotropy in a second order interaction. Yeah. So we have for set up our close coupling calculation, we need also short-range interaction potentials. Of course, we don't know them very well, but we sort of introduced, we first calculated some potentials for both atoms, interacting atoms, and then we introduced them in such a form that easily could be a link to the long range. So, for example, these coefficients, it's a tensor form, but these coefficients, for example, is a function of R. So when you increase distance between atoms, it smoothly connected to Wonder-Wise potentials. So there is it's kind of, you can see how many of them for erbium, for example. So I just want to say that in all these ultracold experiments, there are specific parameters related to ultracold experiment. For example, density of atoms normally ranges between 10 to 12 to 10 to 15 out of centimeter cube, and it's give us idea that between atoms we have like 100 nanometer distance. So that's how you can expect. So temperatures nanokelvin, microkelvin. So, but at the same time, short-range isotropic atom-atom interactions are characterized by S-wave scattering length, typically 5 nanometer. So there is a big difference between 100 and 5 nanometer. So certainly, if we want to have strongly interacting gas, then we have to increase scattering length. And the one way to increase scattering length in very convenient, very nice way is use magnetic Feshbach resonances that we love to increase and then create a strongly interacting quantum gas of atoms. So a few words what is Feshbach resonances. Here's a simple picture, schematic kind of picture of interacting potentials. So when atoms come close together, they sort of create a quasi-molecule that could be described with all these potentials, right? As a function of internuclear separation. So normally atoms are prepared in open channel here. When they enter, they come closer and closer together. And in course of collisions, coupling between close and open and closed channel could happen. So when we change magnetic field, it shifts bound levels up. And when any bound level crosses entrance channel, open channel asymptote, Feshbach resonance can appear. So, but at least in order to have Feshbach resonances, we have to have 2 channels at least. One channel doesn't produce Feshbach resonance. So, but nature of Feshbach resonance for bosonic magnetic atoms is absolutely different from alkali metal atoms. In alkali metal lattice, a hyperfine interaction between electron and nuclear spin provides sufficient complexity so that Feshbach resonances appears even you don't need anisotropic coupling. Mostly it's S-wave Feshbach resonances. For heavy alkali metal molecules, there is a substantial second-order spin orbit which actually provide coupling with other partial waves, and S-wave is other partial wave, and then we will have like non-S Feshbach resonances. But anisotropy could play some role, but very, very small role, and sometimes these resonances are very difficult to observe due to anisotropy. But here, in our case, there is no hyperfine structure for bosonic atoms. So dysprosium and erbium. So the only anisotropy could couple Zeeman sublevels and allow Feshbach resonances to appear. And I think it's interesting that this is sort of constructive effect of anisotropy. Quite open anisotropy is something we don't like, right? It gives us decoherence effects and so on. But here it's really important, property. So what we can do with Feshbach resonances, I already said, so they could convert weakly interacting gas of atoms to strongly interacting gas of atoms. Then they also allow to create molecules in Bose-Einstein condensate from weakly bound molecules. Then which is supposed to be stabilized later using like styrofoam and whatever. Alternatively, interaction can be turned off altogether with Feshbach resonances to create ideal Fermi or Bose gas, for which thermodynamic properties are known analytically. And then for fermionic atoms, phase transitions and universal many-body behavior is predicted. Is studied using Feshbach resonances, as finally free-body ephemeral physics can be explored, certainly, but not yet. So it's people, I think people already working on it.
Will all of those advantages be applicable to these things like erbium? Or
Yes, right.
the dipole interactions
Yeah.
change the story? I mean,
That's
the
what.
dipole interactions make some of those.
Yes, that's a good question. And there's Chris Green paper, right? They already started to look at the ephemeral physics with dipolar gases. It is not related to erbium or particular, I think, system, but they certainly discuss it. And they even say it's more even stable situation for dipolar gas and to create ephemeral states. But you need to select light, probably resonance. And it's already known, the spectrum is known. There are resonances observed. So it's a good time maybe to go to this field. So we performed a close coupling calculation, first principle for interacting dysprosium and erbium based on atomic basis set, the projection MA and B along magnetic field direction now. So we include Zeeman rotation interaction, and they are diagonal, and they don't couple states. But very short range potential is the anisotropic forces can couple different Zeeman sublevels. He is a Hamiltonian, so it's pretty much maybe conventional, but we just want to say the total projection, M, total we call, is conserved. Whenever atom, two atoms colliding and there are transitions to or coupling to other states, this selection rule should be considering this value, right, for erbium, and this is for ytterbium or for dysprosium. So here's the results for long-range potential energy curves, for example, for dysprosium. Two dysprosium are bosonic atoms. So here's 91 diabatic channels. So here is the entrance channel, and there are different Zeeman sublevels higher in different MJ projections for them, and each of them have different magnetic moment, which is described by MJ. So, and for each a limit I would say magnetic limit, there are a few partial waves could be dissociated. So we converged our system for using 10 partial waves. That's why we have these 10 potentials. And of course, S wave, entrance channel actually S wave for temperatures, very low temperatures. I think it's a few nanokelvin or microkelvin anyway. So it's only S wave entrance channel here. But anisotropic interaction could actually mix S2 different partial waves or mix with different Zeeman sublevels. So here's a Feshbach spectrum that what we calculated, right? This is upper panel shows elastic rate, and that lower panel is scattering length, as a function of magnetic field. And we identify that there are D wave and G wave resonances, several actually. But on the right-hand side of this slide, I show experimental observation of Feshbach resonances, which had been done just a few months ago. This published recently. And they observed many more Feshbach resonances than we obtained in our calculation. But first of all, our calculation was performed for very low temperatures, which was used to create BEC for dysprosium. But then, of course, to perform experiment to observe Feshbach resonances is probably extremely difficult to create each time BEC when they change magnetic field. So they perform experiment for much higher temperatures, 400 and 800 nanokelvin. So, but at the same time, I think now we are thinking, of course, we have to adjust our experiment, theoretical model to experimental observation, and we believe that our anisotropic value is not high enough to produce so many resonances. And that, of course, we also believe if we increase temperature, we can do it in our model, then possible that could be some non-zero partial waves and transchannel appear, which could produce many more resonances.
I would have thought that as you increase the temperature, you wash out Feshbach resonances, smear them out so you don't see them.
Not that kind of temperature washout, not yet.
So as you
400 nanokelvin will not
as you
wash
increase
out.
temperature, you can see more and more Feshbach resonances?
In principle, yes.
Well, in this case, it's sort of in between. You see they get bottom panel,
Little.
800 nano, they get a little bit wider. So if they go maybe twice the design temperature, then
Yeah.
everything will wash out.
So when you go from 400 to 800, you see more resonances. When you go to 1600, you see fewer?
They haven't done the experiment.
But that's what you should see.
Yes.
Eventually, you see fewer.
Yes. But I mean, fewer, or you could say they go so close together that they become one blob.
Yeah.
Yeah, but
I mean, I would think, doesn't temperature
It does.
broaden them, and so they?
they not critical yet,
It's
right?
actually
Of
nice
course,
when
if
I
you
see the
increase
graph, I
many
see
more.
resonance.
Yeah.
Mhm.
But if you compare to the kind of match, some resonances which you find.
No,
in
I
the-
cannot even hope on the being in exact location. For this, we have to know short range potentials exact, not only spectroscopically, but really good knowledge about spectroscopic structure from experiment.
So notice the difference in horizontal scale. One is, the theory is 300 Gauss and the experiment is 6 Gauss.
Wow.
Yeah.
So you can't identify the different resonances on the experimental side? Say which one is a D wave, a G wave, or is it possible to?
For this reason, I will show a bit later, I believe that experiment has to perform additional work in order to simplify identification. For example, measure magnetic moments. It will be with, I mean, for Erbium, it has been done, and we done identification, we done this work. But here is just recently observed, they didn't do it yet. Otherwise, we have to really know short range physics, like 81 potentials exactly, up to very high, vibrational levels, in order to put in our code and then calculate the position of Feshbach resonance and be exact. It's extremely difficult. For alkali metal, it's been done for a few cases where only 2 potentials at the short range.
But looking at your theoretical results, there seems to be some gap for instance, between the D wave and the G wave. It's not, and this
Better-
was
better
completely
look-
random.
Better go on to the Erbium result.
Yeah,
That's
right,
more
right.
interesting.
Yeah.
Or maybe clarify
Yeah, so
something.
take a look at the time, and I think you want to bring
Oh,
the main
yeah,
point
yeah.
across.
I'm sorry. Yeah, the only thing I want to say that when we cancel anisotropy and dispersion, or dipole-dipole interaction anisotropy, spectra is changing. So they're both important. Okay. So here's our theoretical calculation of erbium, Feshbach, and then this is experiment by Francesca's Svetlana group, where this is for one isotope, this is for other isotope. You can look maybe at this isotope. So there are many resonances, extremely large number, but temperatures were similar, right? We done the same, temperature, but we were able to go through only up to 20 partial waves. We couldn't increase more. It's a problem with computer kind of problem. Here is also important. Here, so the same idea, what I told, answering your question, that quantitative reproduction of experimental spectra required knowledge of short-range potentials, which now unavailable. So we perform random matrix theory analysis and distribution of magnetic field separation between neighboring Feshbach resonances and compare this analysis with experiment. So here's a graph. Shows, so like a probability to find a Feshbach resonance in a specific parameter S, which is nearest neighbor spacing divided by mean separation. So our experimental data, shown this by blocks, actually fits to red curve, and our close coupling calculation fits to green curve, which actually coincide very much most of the time here. If we plot a Wigner-Dyson distribution, this is a dashed dotted line. It's different, but very close. But Poisson distribution is far away. So it's what it suggests, that in our system, there are, there is a strong interaction between particles. That's sort of, it's a broad distribution, but closer to Wigner-Dyson than to Poisson distribution, when particles should be independent. What we didn't like, that we couldn't increase partial way numbers in our calculation in order to be happy and exactly, fit experiment.
So what, why does it fit so well? For Dysprosium, you said you don't have a good handle on the theory, but then for Erbium, say magically, you get good agreement. Is it magic, or is this an accident, or do you know why?
We worked on Dysprosium more, or Erbium more, since we communicate with experiment. We use the same temperature. So we may be better in sense of anisotropy. What we calculated, which is much larger. Remember, it's much larger than Dysprosium anisotropy, and it's probably better obtained. So we have to go back to Dysprosium and see how. Of course, we cannot change by hand, but we need to find some more experimental data which allow us to improve, knowledge. So here, just we also develop random quantum defect theory in order to look at the asymptote, how to increase number of partial ways in our calculation. and that unfortunately I have to finish. So here, analytical sort of quantum defect theory curve, it's a black curve, and couple of channel, couple of channel calculation of the dots, blue dots. So they pretty much coincide. So it's simple theory what we use to understand how mean resonant density depends on the maximum of the partial wave maximum. So of course we use with some contribution from all partial wave up to L maximum. So they sort of lie, on the top of this curve. But here, for the quantum defect theory, we were able to go much higher L max, and we found in order to match a number of, how many resonance should be for one Gauss, it's like 3 point something observed in experiment. And here we also find these curves converging to this value. And so the conclusion is that actually, in order to perfectly describe, at least in statistical model, this experiment, we really need to increase number of partial waves to ridiculous value, which nobody done it yet. So we just published paper recently in Nature about it. So here's a few words how we calculated magnetic moments for erbium. And as I say, it's very important characteristic to identify resonances. Here's a spectrum from experiment, few Feshbach resonances. It's very low magnetic field. And they managed to measure using magnetic field modulation spectroscopy to measure binding energies of Feshbach molecules as a function of magnetic field. And the slope each of this binding energy changing give you a magnetic moment. And you can see very interesting things, that different Feshbach resonances have different magnetic moments. In principle, you can think, two atoms with magnetic moment 6, right? Or 7, right? 7 and 7, they come together probably 6, it should be 14 Bohr magneton. It is not. His could be 11.3, 10.5, even 7.96. So we looked at the adiabatic potentials as a function of interatomic distance. And of course, when this is entrance channel, and of course the other all potentials are closed channels. And when they cross together at the zero level, Feshbach resonance could appear. And at this point, V equals 0 potential, we call it a closed R star equals 0 potential, we take a derivative from this potential as a function of B, and then we find magnetic moment at this point for different resonances, all these resonances, for particular magnetic field of resonance, right? So from other hand, magnetic moment, talking about anisotropies we discussed before, is actually a sum of the different contributions from Zeeman sublevels, whatever they are, they mixed somehow. So that's linear combination of magnetic moments, and each Zeeman sublevel has different magnetic moment. The lowest is the largest, and then smaller and smaller, and of course it goes up to 0. So, and we checked how these values of magnetic moment depends if we artificially change isotropic C6, anisotropic C6, and then change sort of magnetic moment, magnetic dipole-dipole interaction coefficient. and it's only magnetic dipole-dipole interaction influence on the magnetic moment value practically. So it's really described. Magnetic moment is a property of the long-range interaction potentials. And here's a sort of a table which shows all these experimental properties for Feshbach resonance observed at 0.9 Gauss, 1.5 Gauss, and so on. Then magnetic moments measured, calculated, and the R star, it actually shows size of the Feshbach molecule. If somebody wants to look at that, that's the size of Feshbach molecule. And that is assignment. And the assignment shows a partial wave, L equals 4 or 2 or 6 even. And then total angular momentum, 12. And projection M I was showing over. Sometimes you cannot tell what is dominant contribution. In this case, for example, they all more or less the same kind of -11, -9. But in some cases, it could be like 80% of certain M, so you can say it here. So here's, okay, if we go further, larger magnetic field, we believe magnetic moments should be atomic kind of related to these values. And then I just say that molecules, Feshbach molecules here, have very large magnetic moments, and the dipole length is large. So it's very interesting to do just experiment many body physics or theory with magnetic molecules. And here I suggest topics for afternoon discussions. Very interesting for me, chaotic behavior of levels of resonances, distribution in atomic or molecular scattering versus a scattering in many strongly interacting nucleons. So it's a low sub-millikelvin energy physics against huge high energy physics. But apparently they are linked together. They have similar properties. So then maybe how effective field theory people discuss here all the time could be related to high-spin atomic systems, and how two-body losses influence on free-body recombination rate. And thank you very much.
Yeah, thank you very much. We have time for one or two quick questions.
Mm-hmm.
We have no quick questions. We save the long questions for the afternoon. And
Okay.
take a 5-minute break. Have Joachim set up, and then you go from there.
Yep.
And we thank Svetlana again. Sorry. Sorry.
Okay, that's okay.
Very nice results.
Oh, yeah, yeah.